In September 1999, a NASA spacecraft reached Mars after about 9 months in flight. Its job was to study the planet's atmosphere, weather, dust, and polar regions. Then, during the maneuver meant to place it in orbit, the signal disappeared. The Mars Climate Orbiter had traveled hundreds of millions of kilometers. It had a scheduled engine burn, it had navigation teams, it had years of planning behind it. But one critical exchange of data did not mean the same thing to every part of the system. The most famous version of the story is short. One team used English units, another expected metric units. That is true, but it is not the whole lesson. This was not a story about one person forgetting how to convert miles to kilometers. It was a systems failure at a critical interface, a failure to carry the correct unit information through a navigation process and to catch the error before the final maneuver at Mars. Mars Climate Orbiter launched on December 11, 1998. It was designed to build a continuous global picture of Martian weather and climate over a full Martian year. Its major science instrument was the Pressure Modulator Infrared Radiometer, or PMIRR. It was designed to measure infrared radiation from the surface of Mars to roughly 80 kilometers above it. From those measurements, scientists hoped to retrieve information about atmospheric temperature, pressure, dust, water vapor, condensates, and the radiative balance of the polar regions. In plain language, the spacecraft was meant to help scientists see Mars as a changing planetary system, not just a set of photographs. It carried a real scientific purpose, and that is why the loss mattered. The mission did not fail because it aimed too high. It failed because the chain of information guiding it to Mars was not protected well enough. On September 23, 1999, Mars Climate Orbiter arrived at Mars. To become an orbiter, it needed to slow down enough for Mars to capture it. The planned Mars orbit insertion burn was a 16-minute maneuver, and it began on schedule. About 5 minutes later, the spacecraft passed behind Mars from Earth's point of view. That kind of temporary radio blackout can be expected during a planetary encounter. But this one happened approximately 49 seconds earlier than anticipated. Then the signal did not return. The next day, JPL appointed the Mars Climate Orbiter peer review team to investigate why communication had been lost. The investigation found that a unit translation failure had produced errors in the mission's trajectory calculations. NASA's current mission history summarizes the problem simply. Ground software used English units, while the spacecraft's navigation system worked in metric units. The more useful explanation is about impulse. Impulse is force applied over time. One part of the ground system supplied a value in pound force seconds. The navigation process expected that value in Newton seconds. Those are both legitimate engineering units, but their numbers are not interchangeable. If the data moves from one system to another without the required conversion, the trajectory model is wrong. That is why NASA forgot to use metric is not a good explanation. The failure was not the existence of two measurement systems. Engineers use different units all the time. The failure was that a critical handoff did not reliably translate and verify those units before the trajectory decisions depended on them. A spacecraft does not need a spectacular error to miss the path it was designed to fly. A persistent calculation error can alter the navigation picture across many decisions. NASA's current account says the unit discrepancy caused trajectory calculation errors that sent Mars Climate Orbiter too close to Mars. That makes the final silence easier to understand. The spacecraft was not simply late or lost in deep space. It was at Mars, beginning the maneuver that had to work, on a path that was lower than intended. Contemporary JPL statements after the loss described a planned approach of about 150 kilometers, a reconstructed approach near 60 kilometers, and a believed minimum survivable altitude of 85 kilometers. Treat those figures as the team's early reconstruction, not as a directly observed flight path. This is where the wording matters. The accessible JPL Special Review Board record documents that the spacecraft was occulted by Mars during orbit insertion and that no contact could be re-established. NASA's current official mission page goes further. It says the investigation found that Mars Climate Orbiter burned up in Mars's atmosphere. The careful way to put those statements together is this: contact was lost behind Mars and never regained. NASA's current retrospective conclusion is that the too low trajectory caused the spacecraft to burn up in the Martian atmosphere. It would be wrong to say controllers watched it burn up, or that a crash site was found. The final event was reconstructed after communication was lost. But it would also be misleading to describe the fate as completely unknown when NASA's present official account states the investigation's conclusion. This mission is often told as a joke about metric and imperial units. That version gets attention, but it hides the useful part. A unit label is not decoration on a number, it is part of what the number means. When a number passes from one team to another, or from one program to another, the interface has to answer basic questions. What quantity is this? What unit is it in? Who converts it? Who checks it? What happens if the result disagrees with an independent calculation? Those are systems engineering questions. The Mars Climate Orbiter loss shows why they matter even when every individual component looks competent on its own. The lesson is not that one person must be more careful. The lesson is that a mission-critical system should be built so that one missed conversion cannot travel all the way to Mars without being stopped by another safeguard. That is an editorial synthesis drawn from the mission. It does not require inventing a villain, and it does not make the event less dramatic. It makes it more useful. The immediate result was the loss of the spacecraft and the loss of the climate observations it had been built to collect. But the mission also left a durable engineering lesson. In a complex system, the most dangerous failure may not be a broken engine or a snapped cable. It may be a handoff that looks ordinary because it happens inside a file, a calculation, or a software interface. The solution is not to assume every future project will use the same units. The solution is to make assumptions visible, make conversions explicit, test critical interfaces independently, and treat unexplained navigation behavior as something to resolve before the last safe decision point. Mars Climate Orbiter was built to help us understand a changing world. Instead, it became a warning about the systems we build here on Earth. A number can be perfectly correct and still be dangerous if the next system reads it in the wrong language. NASA's current account concludes that the spacecraft burned up in Mars's atmosphere. The deeper story is what happened before that final moment. A critical unit translation failed, and the mission did not catch it in time. That is why this mission is still remembered, not because metric beat imperial, but because every ambitious system eventually depends on a boundary where one piece of knowledge becomes another piece of action. And if that boundary is not understood, even a spacecraft that reaches Mars can still be lost.